A supernova explosion that vanished will resurface in 2037. A team of astronomers published a study in the journal Nature in the first days of September, predicting that in 2037, a supernova exploded 10 billion years ago on the other side of the universe, and whose light had already been captured by the Hubble telescope in 2016. When presented in this manner, the news may appear extremely intriguing. How is it possible for the same star to explode twice? We are not discussing a recurrent nova, which turns on at intervals of years or decades, but rather a true strong supernova. And supernovae are stars that fully destroy themselves, with no chance of rebirth. Furthermore, how can scientists claim to know even the year in which the supernova appropriately named Requiem will reappear? What do you think? Mirages abound in the sky, stars that appear where they should not, images that split multiple times, and galaxies that twist and thin like threads. The dance of pictures, like in a big kaleidoscope or hall of mirrors, is determined by how we are aligned with distant sources. However, the illusions in this scenario are caused by the gravitational attraction of stars and galaxies rather than mirrors or prisms. Because gravity, like a lens, works on light beams, deflecting them. But you could argue to feel gravity, you need mass and light has none, so how can it experience gravity? This is one of several notions of relativity that are unfortunately understated. Gravity is not, as Newton stated, the impact of a force, but rather the influence of the curvature of the space-time sheet. And everything in the universe is obliged to follow the ripples of space-time. Everything, including light. It is simply impossible not to follow the sheet's folds. The deflection of light by a huge mass is analogous to the behavior of a lens deforming an object's picture. Until 30 years ago, these gravitational lensing occurrences were regarded theoretical oddities. Today, however, hundreds of them have been identified thanks to devices such as the Hubble Space Telescope. They are also extremely valuable for studying the distribution of matter and gravity in the universe. Johann Georg von Sodder, a German astronomer, discovered in 1801 that gravity could deflect light. What had previously been a theory became a certainty for Einstein. Matter has a gravitational attraction that also affects on light, curving its path. Einstein's calculation predicted a two-fold increase in intensity over what Newton's law of gravitation predicted. And it was proven right in 1919, in a famous experiment led by Arthur S. Eddington. The position of stars near the Sun, as observed by Eddington during an eclipse, is somewhat altered because our star's gravity deflects light beams that pass close to it. In practice, it is a mirage similar to those seen in the desert, except that the light rays bend as they pass between layers of air with varying temperatures and densities. This is why a vision of an oasis which exists but is elsewhere can appear where there is simply sand, for example. However, the Sun's gravity is insufficient to produce dramatic optical phenomena. The first true gravitational lens was discovered and identified in 1979 by astronomer Dennis Walsh of the Jodrell Bank Observatory in the United Kingdom. Walsh observed two quasars extremely distant, primordial, and very bright galaxies that were angularly quite close and appeared to be equal, one of which showed out barely on the edge of a galaxy much closer to us. After a brief moment of confusion, Walsh realized that these were two images of the same quasar, which had reached him via two separate optical paths, one direct and one deflected by the gravity of the galaxy, which was at an intermediate distance. It was the first, and it caused quite a stir, but today we have hundreds of gravitational lenses, some of which are far more dramatic, capable of doubling, quadrupling, or sixfolding the image of distant sources. But are we certain that we have fully comprehended the mechanism underlying this amazing cosmic phenomenon? Before delving into the supernova Requiem, it's important to brush up on your theoretical knowledge. To comprehend the nature of these events, it is necessary to begin with certain cosmological concepts. A huge part of the universe appears homogeneous and isotropic when viewed from a distance. This attribute of the universe has been elevated to the status of cosmological principle, and serves as the foundation for the model used by cosmologists to describe spacetime, which is a four-dimensional space comprised of time and three spatial coordinates. This model, for example, can be used to compute the distance traveled by a photon from the instant it is emitted from a light source to the instant it is received by an observer. Furthermore, the photon's course in spacetime may be predicted. Consider instead what actually occurs in the vicinity of a massless body. As we know, a gravitational field forms around it, with the intensity decreasing as the distance rises. As a result of this disruption, the path of light changes with regard to its initial trajectory, focusing rays on the observer that would not have been conceivable in the absence of mass. The effect produced by the presence of a celestial body is thus comparable to the refraction produced by a common optical lens. Just as light propagates through the latter at a different speed than in vacuum, light propagates slower in the presence of a gravitational field, as if photons were attracted by the mass that produces the gravitational field. This resemblance also explains the phenomenon's name, gravitational lensing. Only in 1916, with the development of the theory of general relativity, could Einstein achieve an exact calculation of the deflection angle of a light ray traveling at a specific distance from a mass. He projected a deflection angle of 1.74 arcseconds in the case of the Sun's subsequent experimental verifications, which began in 1919, have fully validated Einstein's prediction. One of the most important proofs of the theory of general relativity is the deflection of light due to gravity. For almost 50 years, the study of gravitational lensing moved slowly, owing to the inability to obtain further observational data. However, it was hypothesized as early as the mid-1920s that one of the consequences of massive celestial bodies deflecting light could be the formation of multiple images of the same source, or even the formation of a ring, if certain conditions were met, such as the circular symmetry of the lens object and its alignment with the source. The discovery of the double quasar, which we have already mentioned, provided a decisive push to the study of lensing in 1979, and astronomers' interest in this phenomena has gradually developed since then. In 1985, an arc structure, the biggest ever discovered with a length of 30, was discovered near the heart of the Abell 370 cluster of galaxies, which is located around 4 billion light-years away from Earth in the constellation Cetus. And it was here that strong lensing was discovered. No one had previously imagined that clusters might have such a dense core that it could generate such an effect. Finally, around the turn of the century, it was discovered that distortion caused by galaxy clusters on images of galaxies behind them is manifested not only by the development of enormous arcs or rings, but also by the appearance of small arcs, a phenomenon known as weak lensing. To summarize what has been mentioned thus far, the elements involved in a gravitational lensing event are three: the astronomical source that emits light, the so-called lens, which is the celestial body that produces the gravitational field with which the light from the source interacts, and finally the observer, who is the astronomer who detects the effect of this interaction with his instruments. The outcome of this contact. These three elements, when combined, form a true optical system. A lensing event is influenced by a variety of elements. First, the distribution of the substance that makes up the lens is critical. In general, when the lens reaches very high mass concentrations at the center, it becomes very efficient. However, much depends on how the source is created. If it is a star or a quasar, i.e. a light source with such small angular dimensions that it can be considered punctiform, the lensing effect is detectable not as a large distortion of the images, which will tend to remain punctiform, but as a result of the appearance of multiple images of the same source. When the lens converges on the observer light rays generated by the source in different directions, multiple pictures are formed. If, as in our case, light beams released by a temporary occurrence such as a supernova explosion collide with differing densities of matter, you can verify the formation of not simultaneous images. Okay, now that we've learned a bit more about lensing, we can move on to the big news: the finding of the Requiem supernova, the forecast of its recurrence, and the cosmic implications of this bizarre narrative. It all starts in 2019, when Danish astronomer Gabriel Branner compares an image obtained by the Hubble Space Telescope during the Requiem, resolved quiescent magnified galaxies program, to another taken in 2016. Incidentally, the reason for the nickname is given here, though as we will see, another astronomer will give it a more romantic spin. The galaxy cluster MAX J0138, depicted in both pictures, is located 4 billion light-years away in the constellation Cetus. It's just a regular comparison, but Branner is surprised to see that 3 points of light emerged in the 2016 shot but were completely vanished in the most current one. Branner immediately dismissed the most outlandish possibilities, realizing that he was witnessing the before and after of a supernova explosion in a galaxy far farther away from the cluster, yet on the same line of sight as the Earth's observer. And that the gravitational lensing that twists the galaxy into reddish arcs is also responsible for the supernova's triple image in the 2016 photograph. Hubble's image of the Max J0138 cluster took around 4 billion years to reach Earth. Based on the distance of its home galaxy, the light from supernova Requiem took an estimated 10 billion years to travel. The supernova then faded until it was completely gone in the 2019 image. This statistic would be fascinating enough on its own, but there's more. Taking a closer examination, Branner and Steve Rodney, an American astronomer, made an astonishing prediction. A fourth image of the same supernova will erupt in 2037, 21 years after the first three. Furthermore, the two astronomers predicted the precise position where the supernova should reappear. Do you want to know how they did it? Well, the team's forecast for the supernova's reappearance is based on computer models of the cluster's gravitational field, which depict the many courses the supernova light takes through the galactic grouping. Each lensed image travels a distinct course through the cluster and arrives at Earth at a different time, owing to changes in the lengths of the supernova light's paths. We can compare the many supernova light trajectories to trains that leave the same station at the same time, travel at the same speed, and arrive at the same destination. However, because they travel on separate length tracks, they will never arrive at the same time. But it isn't all. The supernova image anticipated for 2037 is further behind earlier photographs of the same explosion, because its light goes directly into the cluster's center, which contains the densest matter. According to astronomers, there will be more supernova resurrections after the one in 2037, beginning with the one in 2042, but it will be too faint to be seen by existing instruments. Perhaps future equipment like NASA's James Webb Space Telescope will be successful. Oh, I almost forgot. According to Steve Rodney, the nickname Requiem means a requiem for a dying star and a sort of elegy for the Hubble Space Telescope, which will no longer be with us to receive the star's light in 2037. Incredibly sad, but also incredibly fitting. Isn't it?